Let us begin very gently, and let us begin with a question that sounds simple at first. What does it mean for a set to have a size? For a finite set, this feels almost too obvious to mention. If there are 3 books on a table, or 7 stones in a row, or 12 students in a room, then the size of the set is found by counting. We move from one object to the next, and eventually we stop. The counting process ends. The final number tells us the size. For finite sets, this is so natural that it hardly feels like a definition at all. It feels like a habit of thought, something we learned so early that it became invisible. A finite set has a size because we can count all its elements and finish. But infinity changes the atmosphere completely. When a set is infinite, we do not reach a last element. We do not finish counting in the ordinary sense. So now we must become more careful. We need a language that does not rely on eventually stopping. We need a way to compare sizes even when the process of counting never comes to an end. And this is where listing becomes the right language for infinity. That sentence is worth hearing slowly. Listing becomes the right language for infinity. For finite sets, size is about how many elements there are. For infinite sets, size is often better understood by asking whether the elements can be arranged into a complete sequence. Can we place them in order so that every element appears somewhere on the list? Can we assign each element a position? First, second, third, fourth, and so on forever. This is the central shift. When we study infinite sets, the deepest question is often not simply whether the set is infinite. The deeper question is whether its elements can be completely enumerated. Can they be listed one by one, with no omissions and no repetitions, in a sequence that continues without end? Some infinite sets can be listed in this way. Some cannot. And that distinction between countable and uncountable sets is one of the great turning points in mathematics. It is a place where our ordinary intuition stretches, strains, and then reforms itself into something wider and more subtle. So let us take our time. Let us move slowly through this landscape, returning to the key ideas again and again until they begin to feel natural. We should first recall the basic distinction between finite and infinite sets. A finite set is one that has an end to its counting. If we list its elements, eventually the list stops. There is a last element. There is a final count. An infinite set is one for which this does not happen. However far we go, there is still more. The list does not terminate. There is no final step. But even this is not yet enough. Not all infinite sets behave the same way. Some infinite sets are infinite in a very orderly sense. They can still be paired off with the natural numbers. They can still be placed into an endless sequence. There may be no end, but there is a first element, then a second, then a third, and so on. Other infinite sets resist this kind of arrangement. They are not merely endless. They are too rich, in a very precise sense, to be captured one by one in a list indexed by the natural numbers. This is why the notion of countability matters so much. A set is called countable if it is either finite, or it can be put into a perfect one-to-one correspondence with the natural numbers. Let us say that again in softer language. A set is countable if its elements can be matched exactly with the natural numbers. One element gets the first position, another gets the second, another gets the third, and so on. Every element appears somewhere. No element is missed. No element appears twice. This perfect pairing is called a bijection. A bijection is a correspondence with 2 features. First, different elements of the set must receive different positions. Second, every position in the list must be occupied by some element of the set. No collisions and no gaps. It is worth repeating that countability does not mean the list is short or practical or easy to write down physically. It means only that such a list exists in principle. If we had unlimited patience and unlimited time, and if we kept going forever, then eventually every element would appear somewhere. So countability is really listability. That is the intuitive heart of the matter. A countable set is a set whose elements can be arranged as first, second, third, and so on. A set is uncountable if this is impossible. No matter how clever the attempt, no matter how systematic the method, no matter how long the list goes on, some elements will remain outside it. This contrast is so important that we will keep returning to it. Countable means listable. Uncountable means not listable. Not just difficult to list, but impossible to list completely in that one-by-one way. The natural numbers are the basic model of countable infinity. They give us the template itself. If a set can be matched with the natural numbers, then it behaves, from the point of view of cardinality, like the natural numbers. And the natural numbers are plainly infinite. There is always another one. We never reach the end. So here is our first example of an infinite countable set, the natural numbers themselves. That sounds almost trivial, and in a sense it is. But it gives us the standard against which all later examples are measured. Now let us move to something that at first seems smaller, the even numbers. The even numbers form a proper part of the natural numbers. They skip all the odd numbers. They seem thinner, sparser, less numerous. Between one even number and the next there is a gap. And yet the even numbers are also countable. Why? Because we can list them in order. First comes the first even number, then the second even number, then the third even number, and so on. More precisely, each natural number points to a unique even number. The first natural number points to the first even number, the second natural number points to the second even number, and in general each position on the list produces exactly one even number. So every even number gets a place, and every place corresponds to one even number. This is a bijection. And so the set of even numbers has the same cardinality as the set of all natural numbers. This is one of the earliest moments where infinity begins to feel strange. A part can have the same size as the whole. For finite sets, that cannot happen. A proper subset of a finite set must be smaller. If you remove elements from a finite collection, you reduce its size. But infinite sets do not obey that finite intuition. An infinite set may contain a proper subset that is still large enough to be put into perfect correspondence with the whole set. This is worth pausing over. The even numbers do not merely form an infinite set. They form a countably infinite set. They can be listed without difficulty. And their apparent sparseness does not make them smaller in cardinality than the natural numbers. So already we are seeing that visual impressions can mislead us. Skipping infinitely many numbers does not necessarily create a smaller infinity. That is a lesson we will meet again and again. Now let us widen the picture and consider the integers. The integers include the positive whole numbers, the negative whole numbers, and 0. They stretch in both directions without end. To the right, they continue forever. To the left, they continue forever. At first this feels more extensive than the natural numbers. The natural numbers only go in one direction. The integers go in two. Surely that must make them larger. But again, cardinality cares not about geometric direction, nor about visual spread, but about listability. Can we arrange the integers in a sequence so that every integer appears somewhere? Yes, we can. We begin with 0. Then we take 1. Then -1. Then 2. Then -2. Then 3. Then -3. And we continue in this alternating way forever. This is a complete list. Every integer appears at some finite stage. None is omitted. None is repeated. So the integers are countable. This example matters because it teaches another important lesson. Countability is preserved even when the set appears to spread outward in several directions. A set may look more complicated or more expansive and still remain countable if its elements can be organized into a complete sequence. Let us pause and reflect. The natural numbers are countable. The even numbers are countable. The integers are countable. So far, every infinite set we have touched has turned out to be listable. This can create a dangerous impression. One may begin to suspect that perhaps every infinite set is countable, and that countability is simply what infinity means. But this is not true. And the moment where that becomes clear is one of the great moments in mathematics. Before we reach that turning point, we need one more subtle idea. We need to understand that density and cardinality are not the same thing. This is a very deep conceptual shift, and it is worth approaching with patience. A set is dense in the real line if between any two real numbers, no matter how close they are, there is always another number from the set. That is what density means here. No gaps in a certain sense. Between any 2 points, the set returns again. The rational numbers have this property. Between any two real numbers, there is always a rational number. In fact, there are infinitely many rational numbers between them. This gives the rational numbers an astonishing kind of abundance. They are everywhere. However closely we zoom in, they are still there. Between any two decimal values, however near, there are rational numbers. So the rationals feel enormous. They feel crowded. They feel overwhelming. And this is exactly why they are such an important example. Because despite this density, despite being everywhere in the line, the rational numbers are still countable. Let that settle in. A set can be dense and yet countable. A set can appear to fill the line with endless richness and still be listable one by one. This is one of the places where intuition must become more disciplined. Density measures one kind of richness. Cardinality measures another. They are not the same. A dense set is not necessarily uncountable. A countable set need not be sparse. The rational numbers prove both points at once. So let us now look carefully at the rational numbers. A rational number is any number that can be written as a ratio of two integers, provided the denominator is not zero. So examples include whole numbers, fractions, negative fractions, and many familiar decimals that eventually terminate or repeat. There are infinitely many rational numbers. That is clear enough. But the surprise is that they can still be listed. At first this seems implausible. Since there are infinitely many integers, and infinitely many possible numerators, and infinitely many possible denominators, it feels as though the rationals should form a much larger infinity. But a feeling is not a proof. And here mathematics teaches us to replace impression with construction. Imagine arranging the positive rational numbers in a grid. Along one direction we place the possible numerators. Along the other direction we place the possible denominators. At each position in the grid sits a fraction. So somewhere in that grid we find 1 over 1, 1 over 2, 1 over 3, and so on across a row. Then in another row we find 2 over 1, 2 over 2, 2 over 3, and so on. Every positive rational number appears somewhere in this infinite grid. Now the question becomes, can we systematically visit all positions of the grid in a sequence? Yes. We move through the grid by diagonals. We first take the entry at the top corner. Then we pass through the next diagonal. Then the next. Each diagonal contains only finitely many entries, so we can finish it and move on to the next one. In this way, every position in the grid is eventually reached. So every positive rational number can, in principle, appear somewhere in an infinite list. There is a technical issue. Some rational numbers appear more than once in the grid, because different fractions can represent the same number. 1/2 and 2/4 are the same rational number. 1/3 and 2/6 are the same rational number. So if we simply read off the grid, we will produce duplicates. But this does not ruin the argument. We can agree to keep only fractions written in simplest form. Or we can pass through the grid and ignore any entry that represents a number already listed earlier. The important fact is that duplicates are manageable. They complicate the bookkeeping a little, but they do not prevent enumeration. So the positive rational numbers are countable. From there it is easy to include 0 and the negative rationals as well. We can interleave them just as we did with the integers, 0 first, then a positive rational, then its negative, then the next positive rational, then its negative, and so on. Thus all rational numbers form a countable set. This is one of the most important examples in the entire subject. Let us say it clearly. The rational numbers are countable, and yet they are dense in a real line. So density does not imply uncountability. This is one of the deepest conceptual corrections that the study of infinity asks us to make. At this point, we have seen many infinite sets that are countable. The natural numbers, the even numbers, the integers, the rational numbers. So now we are ready for the real turning point. We turn our attention to the real numbers, and in particular to the numbers lying strictly between 0 and 1. This is a very small interval in the geometric sense. Its length is modest. It is just one little segment of the real line. But the question is not geometric length. The question is listability. Can all the real numbers between 0 and 1 be arranged into a single complete sequence? If the answer is no, then something remarkable follows immediately. If even this tiny interval is already too large to list, then certainly the entire real line is uncountable as well. So the interval between 0 and 1 becomes a perfect testing ground. If countability fails there, it fails in a dramatic and decisive way. And this is where Cantor enters. Cantor's diagonal argument is one of the clearest and most beautiful proofs in mathematics. Not beautiful in a decorative sense, but beautiful in the sense that it changes what we believe is possible. It shows that the real numbers between 0 and 1 cannot be listed completely. Not that we have not yet found the right list. Not that the task is difficult. But that it is impossible in principle. Let us go through the argument slowly. Assume, for the sake of contradiction, that all real numbers between 0 and 1 have been listed. So imagine a long infinite list. In the first row is the first real number in the interval. In the second row is the second real number. In the third row is the third. And so on forever. Now write each number in its decimal expansion. So each row becomes an endless string of digits after the decimal point. The first row might begin with certain digits. The second row might begin with others. The third row with others again. We do not care what the actual digits are. We are assuming only that every real number in the interval appears somewhere on this list. Now comes the decisive step. We construct a new real number by looking along the diagonal of the list. From the first listed number, we look at its first digit after the decimal point. From the second listed number, we look at its second digit. From the third listed number, we look at its third digit. And so on. So we are reading one digit from each row, always moving one step farther along in the decimal expansion as we move downward through the list. Now we build a new number digit by digit. For the first digit of the new number, we choose something different from the first diagonal digit. For the second digit of the new number, we choose something different from the second diagonal digit. For the third digit, something different from the third diagonal digit. And we continue forever. We can do this systematically in a simple way. For example, whenever the diagonal digit is not a certain chosen value, we replace it with that value, and whenever it is that value, we replace it with another safe value. The exact rule does not matter very much. What matters is that the new digit always differs from the diagonal digit in that position. As a result, the new number differs from the first listed number in the first decimal place. It differs from the second listed number in the second decimal place. It differs from the third listed number in the third decimal place. And in general, it differs from the nth listed number in the nth decimal place. So this new number cannot be equal to the first listed number, because they disagree somewhere. It cannot be equal to the second listed number. It cannot be equal to the third. It cannot be equal to any number on the list. And yet we constructed it as a real number between 0 and 1. So the list was not complete after all. That is the contradiction. We began by assuming that all real numbers between 0 and 1 had been listed. But from that very list we produced a new number missing from it. Therefore no such complete list can exist. The interval between 0 and 1 is uncountable, and therefore the set of all real numbers is uncountable as well. It is worth repeating why this proof is so powerful. It does not merely show that one particular list fails. It shows that every possible attempted list must fail. That is the force of the argument. You bring me any proposed enumeration of the real numbers in the interval. Any one at all. It may be ingenious, systematic, highly structured, wildly creative. It may have been designed with every precaution. It does not matter. From that very list, the diagonal method manufactures a new number that escapes it. So uncountability is not just a statement about our limitations in practice. It is a theorem about the structure of the set itself. The real numbers resist every conceivable one-by-one enumeration. This is one of the clearest moments in mathematics where proof changes our picture of reality. Before the proof, one might vaguely imagine that all infinities are similar and that with enough cleverness everything infinite could be listed somehow. After the proof, that belief cannot survive. Some infinities fundamentally cannot be captured in sequence. Some infinities overflow the format of listing. And the reals are the central example. Let us pause and reflect. We now have a sharp distinction. Some sets are countable. Their elements can be arranged into a sequence indexed by the natural numbers. Finite sets belong here, and also many infinite sets, the natural numbers, the integers, the rational numbers. Other sets are uncountable. Their elements cannot be exhaustively listed in this way. The real numbers belong here, and already the tiny interval between 0 and 1 belongs here. So the phrase uncountable does not merely mean very large in a vague emotional sense. It means not listable. It means no bijection with the natural numbers exists. Now another phrase enters naturally, the continuum. The continuum is the cardinality of the real numbers. In other words, when we speak of a continuum-sized set, we mean a set that has the same cardinality as the real line. This is a specific infinite size. It is not just another word for enormous. That distinction matters. A set can be uncountable without us immediately knowing where it stands among the possible uncountable sizes. Uncountable does not automatically mean larger than the continuum in the strongest sense. It simply means not countable. The continuum is one particular uncountable cardinality, namely the cardinality of the real numbers. So we now have at least two levels of infinity clearly before us. There is countable infinity, exemplified by the natural numbers. And there is the continuum, exemplified by the real numbers. Already the infinite world is layered. It is not a single undifferentiated vastness. It has structure. It has hierarchy. It has more than one size. At this stage, Cantor's diagonal argument may feel like a miracle that belongs only to the real numbers. But in fact it is part of a much broader theorem. To see that, we introduce the idea of the power set. Given any set, its power set is the set of all subsets of that set. So if we begin with some collection of elements, the power set gathers every possible selection of those elements. The empty subset is included. Single element subsets are included. Larger subsets are included. The whole set itself is included. Every subset belongs. And Cantor's theorem says something astonishing and completely general. For every set, the power set has strictly larger cardinality than the set itself. No set can be put into one-to-one correspondence with the collection of all its subsets. This is another place where diagonal thinking appears. The proof again constructs an object that escapes any proposed correspondence. The details differ slightly, but the spirit is the same. Given any attempted matching between elements and subsets, one defines a special subset by reversing membership along the diagonal, and this new subset cannot match any element in the proposed list. So the power set always climbs above the original set. This means that infinity does not stop at two sizes. Starting from any set at all, we can form a strictly larger one by taking all its subsets. If we begin with the natural numbers, which are countably infinite, and then take their power set, we get a strictly larger cardinality. And remarkably, the power set of the natural numbers has the same cardinality as the real numbers. So the continuum can be understood in this way as well. It is the cardinality of all subsets of the natural numbers. This links the countable world and the uncountable world in a very deep way. From the natural numbers, by taking all possible subsets, we rise to a strictly larger infinity, the infinity of the continuum. So again, the message is clear. Infinity comes in levels. And the power set operation is one of the engines that generates higher and higher levels without end. Let us now contrast some important examples very explicitly. The rational numbers are countable. The real numbers are uncountable. This alone already tells us something profound about the irrational numbers. The irrational numbers are those real numbers that are not rational. They are what remain when the rational numbers are removed from the real line. Now since the rational numbers are countable and the real numbers are uncountable, removing the rational numbers from the real numbers still leaves an uncountable set. Why? Because deleting only countably many elements from an uncountable set cannot reduce it all the way down to countability. So the irrational numbers are uncountable. This is worth stating plainly because everyday intuition often gets it backward. Many people first meet irrational numbers as unusual creatures, square roots of non-square whole numbers, or the famous constants from geometry and analysis, or non-repeating decimals that seem somehow exceptional. But from the point of view of cardinality, the irrationals are not rare at all. They are the overwhelming majority of real numbers. The rational numbers, despite their density and familiarity, form only a countable subset of the real line. The irrationals vastly outnumber them in the sense of cardinality. So again our intuition must adjust. The rationals are everywhere, yet countable. The irrationals are what remain, and that remainder is uncountable. The real line is, in a cardinal sense, dominated by irrationality. There is another beautiful application of countability that leads to one of the most magical conclusions in mathematics. Consider the algebraic numbers. An algebraic number is a number that satisfies some polynomial equation with integer coefficients, where the polynomial is not the zero polynomial. Examples include rational numbers, many familiar roots, and various numbers that arise naturally in algebra. Now there are infinitely many such polynomials. There are also infinitely many algebraic numbers. One might imagine, once again, that this collection is so rich that it should already fill most of the real line. But it does not. The algebraic numbers are countable. Why is that? because the set of all polynomials with integer coefficients is itself countable. One can list them by degree and by the size of their coefficient. There are infinitely many, yes, but they can be arranged into a sequence. And each non-zero polynomial has only finitely many roots. So the collection of algebraic numbers is a countable union of finite sets. An accountable union of finite sets is countable. Therefore the algebraic numbers form a countable set. Now compare this with the uncountability of the real numbers. If all real numbers were algebraic, then the reals would be countable. But they are not. They are uncountable. Therefore most real numbers are not algebraic. They are transcendental. A transcendental number is a number that is not the root of any non-zero polynomial with integer coefficient. So transcendental numbers are not a few exotic curiosities scattered sparsely through the number line. On the contrary, they vastly outnumber the algebraic numbers. This conclusion is one of the most astonishing in the whole story. Numbers defined by polynomial equations feel concrete, structured, expressible, perhaps even central. But in the cardinal sense, they form only a countable island inside the uncountable sea of the reals. Most real numbers are transcendental. Most real numbers cannot be captured by polynomial equations. Most real numbers lie beyond that entire algebraic framework. This is one of those truths that changes the atmosphere of mathematics when one first really absorbs it. Let us pause again and gather the main ideas. A set is countable if it is finite, or if its elements can be arranged in a complete sequence indexed by the natural numbers. This means there is a perfect one-to-one correspondence with the natural numbers. Every element gets a place first, second, third, and so on. No omissions. No repetitions. That is the formal idea. And the intuitive image is the image of listability. The natural numbers are countable. The even numbers are countable. The integers are countable. The rational numbers are countable. Even though the rationals are dense, they are still countable. So density and cardinality are different notions. Then Cantor's diagonal argument shows that the real numbers in the interval between 0 and 1 cannot be listed. Therefore the interval is uncountable, and so the real line is uncountable. This gives us a new infinite cardinality, the continuum. Then the power set theorem shows that for any set, the collection of all its subsets is strictly larger in cardinality than the set itself. And finally, we see that the irrational numbers are uncountable, while the algebraic numbers are countable, so most real numbers are transcendental. These are the landmarks. And it is good to hear them more than once, because this subject has a way of slipping past attention if heard only quickly. Let us now return one last time to the emotional and philosophical heart of the matter. At first, infinity can seem like a single blur, a vastness, a never-ending continuation, something too large to grasp, but still somehow uniform. What the theory of countable and uncountable sets reveals is that infinity is not one thing. There are infinities that we can organize one by one. There are infinities that resist every such attempt. There are infinities that arise as power sets of other infinities, always pushing beyond what came before. So infinity is not merely endlessness. It has internal structure. And perhaps the most beautiful lesson in all of this is that mathematics reaches these truths not by vague metaphor, but by exact argument. The difference between the rational numbers and the real numbers is not a matter of mood or appearance. Both are infinite. Both are crowded into the line. Both seem abundant beyond ordinary imagination. And yet one is countable, while the other is not. The difference lies in whether a complete enumeration exists. That is the thread that holds the whole topic together. Can the elements be assigned positions in an endless list? If yes, then the set is countable. If no, then the set is uncountable. This simple question becomes a doorway into one of the deepest reorganizations of mathematical thought. It teaches us that not all infinities are equal. It teaches us that listing is a profound test. It teaches us that abundance can mean different things: density, cardinality, algebraic describability, topological richness. These are not the same, and mathematics becomes more beautiful as we learn to distinguish them carefully. So if your mind has drifted, let us end by returning to the clearest possible summary. A finite set is one whose counting ends. An infinite set is one whose counting does not end. A countable set is one whose elements can still be listed in principle first, second, third, and so on forever. A bijection is the perfect matching that makes such a listing exact. The natural numbers give the basic model of countable infinity. The even numbers, the integers, and the rational numbers are all countable, even when this initially feels surprising. The rational numbers are dense, but still countable. So density does not mean larger cardinality. The real numbers, already within the interval between 0 and 1, are uncountable. Cantor's diagonal argument proves that no complete listing of them can exist. The continuum is the cardinality of the real numbers. The power set of any set is always strictly larger than the set itself. The irrational numbers are uncountable. The algebraic numbers are countable. So most real numbers are transcendental. And beneath all these facts is one common, guiding idea. To understand infinity, we ask whether it can be listed. That question is quiet, almost modest. And yet from it emerges an entirely new universe of sizes, structures, and possibilities. Let us leave the subject there in that quiet place. Not with a final image of chaos, but with a feeling of order. Not with infinity as a blur, but with infinity as something shaped, layered, and noble in part. And perhaps that is one of the gentlest gifts mathematics offers. Even when something cannot be finished, it can still be understood. Even when something has no end, it can still have form. And even among the infinite, there are distinctions delicate enough and powerful enough to change forever the way we think.